Hello everyone, my name is DS Duke, and today I'm going to show you how I made a retopo tool in XSI using ICE for some guys at work. Now first, before I get started, just want to let you guys know that I'm a programmer. I'm not a 3D expert or professional or any of that. I write software, but I do enjoy working in 3D, and I'm pretty good at ICE sometimes. Alright, so basically you have a grid and a sphere, and your grid conforms to your sphere and conforms to the closest points on the surface of your sphere, and you can move it around and you can go into it, go into edge edit mode, and you can start moving points and they'll conform. As you can see, something weird's going on with my points because I don't know what I'm doing, and also can't move my stuff up and down. But yeah, that's basically how it works. And come out of there. Alright, you can come out of there, and you can also move that around. But today I'm going to show you guys how I got this far. And it's not done, by the way. There's a lot of stuff that can be added, but it should serve as a good basis for you guys to make your own projects. Alright, so starting fresh. The first thing we want to do is create or import a high resolution mesh, but I'll just keep it simple and we'll start off with a torus. And I like to up the divisions on there because I want to, have some more geometry to play around with, and we're trying to simulate a high resolution mesh, so it's better to have more points. And the next thing you want to create is a grid, and we're going to use the grid just default points, the same amount of points it starts with, but typically, when you do retopology, you guys probably already know this, but you want to start off with the grid that you want to start off with a grid that has fewer points, just so that it's easier to move things around to get a default position, but whatever. So rotate that into place, and what we're going to do is we're going to project the points from the grid onto the closest locations on the torus. But before we actually apply deformations, we're going to visualize what's going on. And in order to do that, the first thing we need to do is create an ice tree, and we're going to need a set data and a pass-through. This way. Alright. And the set data is what allows us to execute whatever we're trying to do in the ice tree, and the pass through is just used for visualization. It keeps everything up to date without having to hit show values again every time. Anyway, so we're gonna call the value for our set data, we're gonna call it self dot project points to surface, and you can name that whatever you want to. I just like to name it something meaningful, so if I ever forget what I was doing, I can always come back later on and see what the variable name is. Alright, so we need to go from the each and every point on this grid. We need to go from there to the closest location on this surface. In order to do that, we're going to use a few nodes. We're going to need a subtract, we're going to need a get data, we're going to need a get closest location, and we're going to need a get point position. And do not worry, I'm not one of those people that just kind of connects everything and blows through it. I'm actually going to try to show you the thought process I used. Oh, and we're also going to need a torus, or we're going to need the node that represents our object. Okay, so we need to get points going from the grid to the torus. In order to do that, we first need to figure out where the closest points are, or the closest location is, on the torus coming from the grid. And to do that in vector math, if you want to vector from one position to a target position, you subtract the target position's vector from the position that you're trying to go to. Okay, this is all makes sense in a minute. So we need to get the closest locations on the surface from the grid. So we want to do that with the get torus and the get closest location node. Pipe the value into the geometry, and the position is the position that we're coming from. So we're coming from all the points on this grid. So pipe the get point position into the position of get closest location. Now we need to subtract our positions of the grid from the closest locations on this torus. But you can't just go from the subtract. You can't just go from the get closest location, because that gives you location data. And our subtract is now expecting vectors, which is what our point positions are. So there's an easy fix for that. We'll just use the get data, pipe the location into the source, double click our get data, and hit Explorer. And as you can see, as I said before, it's giving you location data. But inside of this location data, you have all this other data that you can use. And so the data that we're interested in is the point position. And now that we have this, we can pipe that into the first position of our subtract, and order does matter here. And then the result we can pipe into our pass-through. As you can see, once you pipe that in there, everything that was red turns a color, which means that everything is fine. So we want to right click on the pipe going from the out of our pass-through into our project points to surface. Go there, hit show values, and we want vectors. Okay. Oh. And there you go. You have points coming from the grid onto the torus. If you move this around, you can see everything moving. But there is a problem. If you look closely while you're moving the torus, you'll see that it's kind of favoring going on the actual edges of the geometry. And then if you look at the points in this area, you see they're kind of popping. And that is because, or I believe that's because, I actually don't know why that is, but just an educated guess, that's because the get closest location is actually returning points in between actual vertices on the object. So our closest locations are always in between 2 points. But we want the closest location on this surface. We don't want the closest location in between points, because then we have unsmooth movement in our retopology. And to fix that, we're going to keep everything that we've worked on so far, and we're going to use that as a to give us a clue of what direction we need to move in.